Hey guys, welcome back. Today let's master Codeforces 1816B-Grid Reconstruction. Consider a 2x grid where n is an even integer. You may place the integers 1, 2, all the way to 2n on the grid using each integer exactly once. A path is a sequence of cells achieved by starting at 1, 1, then repeatedly walking either downwards or to the right and stopping when 2n is reached. The path should not extend beyond the grid. The cost of a path is the alternating sum of numbers written on the cells in a path. That is, let the numbers written on cells be A1, A2, all the way to AK in the order that is visited. The cost of the path is A1 minus A2 plus A3 minus A4, yada yada yada. Construct a way to place the integers from 1 to 2n on the grid such that the minimum cost over all paths from 1, 1 to 2n is maximized. If there are multiple such grids, print any of them. And then we just take in some basic input, a t for test cases, and then an n, right? I've already gone ahead and did that. Now first, let's just examine the test cases just to understand what's going on. We need to build a 2n grid, right? So for the first test case, n equals 2, so we build a 2 by 2 grid. And that's exactly what we've done here. And then we are allowed to move either to the right or down. In this first case, they show a case of going down, then to the right, so 3 to 1, then 1 to 4. Second case, we go to the right, 3 to 2, then down to 4. So, yeah. Now, what can we notice about this question? We want to maximize the minimum cost, right? And in order to do that, let's just build a box with, I don't know, let's say n equals 6. So our max values are going to be 12 and 11, right? Or like 2n and then 2n minus 1. And let's just build this real quick. Bang, 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 bang. So in order to maximize our minimum cost, we can kind of do this sort of optimization for all possible paths created. Where can we put our highest numbers such that all possible paths need to use them, right? Well, all possible paths will need to use our first square as well as our last square. So if we just did 2n and 2n minus 1, either or works in either square, but for implementation's sake, I'm going to do it like this, and I'll show y'all why later. Like, now every path has to use these two numbers. The next thing to notice is based on this kind of behavior where we swap the 1s and 2s, or like we add, like if you just take a look, we add all the odds, we subtract all the evens behavior, we can quickly see that so our first grid is going to be even, or we're going to be adding. We can either go down to or to the right, but either choice we have to subtract these. So these have to be subtraction. And then if we're on this square here, going over here would be adding, going down would be adding. If we were to go over here from this square, we would need to add as well. So you can quickly kind of see that it's this checkered pattern of addition and subtraction behavior on the grid. Now, in order to maximize the minimum, let's consider a case where we just maximize the maximum. And we can do that by making all our positives the big numbers and all our negatives the small numbers. And especially this first row, let's keep it simple and let's just pick this to be our maximum path. In order to do that, we would put like 12, 11, well, I guess 11's already taken, so the next is 10, 9, and then we would put like 1, 2, 3 here. This would be our maximum path, right? All the biggest numbers are being added, all the smallest numbers are being subtracted. But then our worst path would be like something like this. Say this was our worst possible path, where we're adding the smallest numbers and subtracting the biggest numbers. Our variance would be very big on our best possible path and worst possible path, or like highest cost path and lowest cost path, right? So we want, in order to maximize our lowest cost path, we have to squish the variance down as much as possible. And for that to happen, we still want on all the plus areas, we want to add big numbers. And on all the minus areas, we want to subtract small numbers. But we should mitigate the distance between our choices. Because if we don't, picking different paths may still have drastically different costs. So in order to minimize this variation, the distance constant between our choices should be as minimal as possible, which in this case will be 1, right? So what does that look like? Let me just visually draw this for you. It means choosing to go right or down should only have a difference of 1 cost. So if you're here, if you're like anywhere on the top, choosing to go right or down should only be a difference of 1. If you're increasing, you're gaining 1. If that makes any sense. Simply because this reduces our variance. Now, let's just write out everything we know. Number 1 we have 2 zigzags. Plus zigzags are big numbers. Minus zigzags are small. Right? Number 2. We want to minimize our variation. So minimize the difference between our choices. All right. Now, let's craft a grid with our newfound knowledge. Bang, 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 bang. I guess we have 2 more points, right? The 2n and 2n minus 1 thing. I won't write those out. I think I explained that enough. So our biggest number, put 12 here, 11 here, right? Now, to minimize the difference, our next numbers here have to be small. What are our 2 smallest numbers? 1 and 2. They happen to have a difference of 1, right? So let's just put 1 here, 2 here. And yeah. Now let's go to our big numbers. So, okay, to help y'all visualize this, let's just draw out our number choices. 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. And let's split these down the middle here. These are our small numbers. These are our big numbers. We've already used 12 and 11. We've used 1 and 2. Our next big numbers are 7 and 8, because these are big squares, remember? Plus. Now we go back to our small squares. 3, 4. Now we go back to our big squares. 4, that's a 6. My handwriting's kind of bad. 6, 10. Now we go back to our small squares. 5, 6. Well, I definitely doubled up some numbers here. Hold on a sec. Let's run it back. 1, 2. Okay, 1, 2, 3, 4, 5, 6, 7, 8. No, this is a 9. 9, 10, 11, 12. Sorry about that. So 1, 2, 7, 8. These are our big squares. And then 3, 4. And then we go back to our big squares. We go 9, 10. And then go back to our small squares. 5, 6. There we go. And that should work. And so, yeah, there's a few things to note about this grid on implementation, and there's a few quirky things that I want to point out. If you check this, our middle, like downwards motions, all have the same value. So it's saying wherever you choose to go down, you will gain the same amount. The only difference is whether we choose this first or last. Sorry, not even the last. The only difference is the first square to go down, right? Because all these are 5. This is 11. Now, that's just kind of quirky. It doesn't really mean too much. But for implementation-wise, what helps us is the tops are all even and the bottoms are all odd. Isn't that unique? So what does that mean? Let's just keep track of two arrays. Even equals, let's just generate a range for now from 1 to n plus 1, and odds equals same thing but from n plus 1 to 2 times n plus 1. Okay, what is this giving us right now? So far, it should just be, in our case, it'd be 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12. But that's not what we want, right? Right. So what we can do is, first of all, let's put 12 at the very front. Just because, like, eventually we want 12 to be here, right? Let's split this. This is a different operation. Let's put 12 at the front. So now we have 12, 7, 8, 9, 10, 11. We can do this very simply in Python with odds equals odds -1 plus odds everything until -1, right? And then if I were to get rid of all this, now all we need to do is kind of just flip the position of every other index, right? So flip these, flip these, flip these, and we kind of just have our answer, right? We can also do this pretty simply in Python with evens 2. Oh. Evens 2. Odds 2 is equal to odds 2 evens 2, like this. And we're just saying flip, like for every other index, flip evens and odds. Yeah, this is basically just doing this, guys. A little bit confusing. Okay, and then let's print out evens and odds, the unpacking operator, because we don't want them in the form of an array. And there you go. The code's actually very simple for how kind of technically complex this question is, which is surprising for 1000 rated. This is, I would say it was a pretty difficult question. I did get it wrong twice. But yeah, and that's the code. And this is my implementation. And it's not going to run case for case because, right, there's multiple solutions. But this is the solution. It works. It's accepted. And yeah. If y'all have questions about this question, leave it down in the comments. I'll try to answer anything. If this helped y'all, great. Let me know. Drop a like, I guess, and subscribe. And I'll see y'all guys next time. Bye.